windows over. Okay. So we are in day, or what is this? Week 15, day 2, our final kind of in-person class like this before our exam. This is our last of 3 review sessions. So today we'll be doing the stuff from after the midterm. So that's sequences, series, interest, and all the calculus stuff that we were learning. So that's our plan. Got a whole bunch of practice questions. That's it. So we'll get started. First one's here. Give you 2 minutes. Try to solve. All right, so we think the first one is 10. So one more time. Negative 98. Okay, so let's look. So we have just 2 kind of random terms in the middle of the sequence. We weren't actually given the first one. So how can we find the first one? $88, $89. Okay, we'll check. What is your strategy first? How can we find the first term if we're given these 2 things? Okay, so our general term formula, we can use that one here. So that is an equals a1 plus n minus 1 d, and we have this information for the 4th term and the 7th term. So for the 4th term, 7 equals a1 plus 4 minus 1, so 3d. And then for the other one, we have 4 equals a1 plus 7 minus 1, 6d. That's two equations with two unknowns. That's very solvable. We could just do elimination here and subtract, and we get 3 is equal to negative 3d. So then d is equal to negative 1. And our d can just go back into either of these other two equations here. So let's say 7 equals a1 plus 3 times negative 1, and rearrange a1 equals 10. Okay, there's the first term. And then the 100th term, it's just the exact same general term formula. So A100 is A1, so 10 plus n minus 1, so 99 times our d value, negative 1, 10 minus 99, so negative 89. C here is maybe a little not something we directly did in class before. So what's your idea for this one? Okay, so we have our formula for the partial sum, n over 2. N over, actually, so a1 plus an, or we have the other formula, which was n over 2 a1 plus n minus 1 d. All right, which of these formulas is more useful for us? Second one, why the second one? All right, we don't know an. If we tried to use the first one, then we have an unknown here. So let's just write out what that would be. We would have 0 equals n over 2. A1 we know, 10 plus an. So we would have one equation with two unknowns, and that's not solvable. On the other side, though, we have 0 equals n over 2. 2 times a1, so that's 20 plus, let's just combine this. Let's skip some steps here. So we would have 20, oh, right, 21. So this is 20, and then here negative 1 times our d, negative 1 would give us a positive 1, so 21, all right, minus n will turn negative there. Okay, so this thing, then how do we solve? Okay, so just when we were doing the kind of solving a quadratic when we did, or the calculus stuff, we have two things multiplied together that equal 0. One of those must be equal to 0. So either n over 2 equals 0, and therefore n equals 0, or 21 minus n equals 0, so n equals 21. N equals 0 doesn't make sense because our sequences start at 1. That's the first kind of counter. So 0 is just not really a possibility. We can just ignore that one. So here's our solution, n equals 21. And we could verify that. So S21 is equal to 21 over 2 times 2a1. We had 20 and plus, or n minus 1. So 20 times negative 1. So that'd be 20 minus 20, that's 0. So yes, the whole thing turns into 0. So we've confirmed our solution. So still just using the same formulas, just maybe we're doing them in kind of a different order or subbing in different parts. But same basic formulas will get us to our solution. All right, take a screenshot if you want it. Next one. Go ahead. Read the interest rate very carefully. I wrote that here. Just keep working. Get the answer first. Are we ready? No? Are we confused? So we've seen two answers in the chat so far. One is 10,000 years. The other was 20 years. Anyone else have a different answer? Not sure. Nine 9.5 years. Okay. All right, let's take a look. So this is, what kind of situation are we dealing with? Simple interest, what's our formula? One plus IT. And in the question, what information were we given? Okay, we'll get to I'll put that in last. So what's the easier information we were given? That's I. We'll get to that at the end. What other information were we given? Principal, okay. So starting value, 10,000 here. All right, and what else? Something else too. AT, so our final value is what? 30,000. Triple in value. So whatever the starting value is, it was 3 times that amount. All right, and our I, tell me what the interest rate is as a decimal, not as a percentage. Okay, 0.0002. So it's 0.02%. To turn that into just a regular number, a decimal, we add 2 more decimal points there. So like I said, read that very carefully. I'll talk about that in a moment when we finish. And the rest, we just want to know what our time is. So put all the parts in. 30,000, 10,000 times 1 plus 0.0002 t. And just divide here. So we get 3 is equal to 1 plus 0.0002 t. So 2 is equal to that. Okay, so we get 1 over 0.0001 is t, and just do that division there. T is 10,000. So there's our solution. I chose this number in particular because for just like a basic bank account, like an everyday bank account, this interest rate is realistic. So if you just leave your money in your regular bank account, it's the worst possible way to invest. It would take, again, 10,000 years just to get 3 times bigger. So terrible kind of investment. All right, so that's that one. Done. All right, next one. Go ahead. You should not need a calculator. The previous question and this one were both designed to be very easy to solve with no calculator. Shouldn't need the calculator. You should not. What's 3 times 32? All right, we're getting an answer. 96 million in the classroom. Same people are, same answer coming in the chat. All right, so let's take a look. What kind of situation are we dealing with? Compound interest, what's that formula? Okay, so close the brackets, then exponent t here outside the bracket. All right, so we're given a principal of 3 million and t of 5 years. What is our interest rate as a decimal? Okay, 1. 100%, that is equal to just 1. All right, and we just put in all the parts. So A3 here is 3 million times 1 plus 1 to the exponent 5. So that's 2. 2 to the exponent 5 is 32. So 96 million. All right. So a nice short question here. Yes, next question. Everyone's ready. Okay, the rest are calculus things. So find each of these, and I hope you remember what these two things here mean. The first two are not so hard. So I'll give you about 2 minutes or 1 minute, 1.5 minutes, solve A and B, and we'll do those. And then I'll give you some more time to do C and D. This is 2 over cube root x. Okay, let's talk about A and B first, and then I'll give you some more time to work. You might not be finished all of them, but A and B, definitely we should be finished by now. So our original function, y is equal to 20 x squared. Let's just step back here. This first one, dy over dx, what does that mean? Derivative, first derivative. D squared y over dx squared, second derivative. Okay, so we have to remember what those symbols mean there. So what is our first derivative here? 40x, and second derivative, just 40. So using our power rule, nothing special happening there. Second one, y is 5x cubed plus 1 over 5x squared plus 23x x. What is our first derivative? 15x squared plus 2 over 5x plus 23. Just using our sum rule now, do each derivative independently and then add them up afterward. Second derivative, 30x plus 2 over 5. That's it. Okay, take some more time and try to solve the last two. We're going to have to remember some exponent rules to solve the C and D here. All right, so let's do C here. Before we do, it is possible. In the last workshop, I showed students a quotient rule. So it is possible to do a derivative directly with this, but it's a lot easier to do some rearranging and then use power rule instead. So if we rearrange this thing, cube root x. Okay, so first thing is a root is the same as a fractional exponent. So x to the exponent 1 over 3, that's the exact same thing. And one more thing we can do. Okay, so if we have any variable here on the bottom, something with an exponent on the bottom, then that's the below on the bottom half of a fraction, then we can change it to just a negative exponent and rewrite it with this. That's the exact same thing. So if we have this, then we can do our first derivative more easily. Negative 2 over 3x to the exponent negative 4 over 3, like that. And second derivative, 8 over 9. Negative 7 over 3. All right. So at this point, we just use our power rule very directly there. Nothing special happening. We just have to remember the exponent rules to rearrange a bit before we can do that easily. All right, the other one, D here. So f of x is 4th root of x to the exponent 15 over 4th root of x to the exponent 5. So we want to simplify this a bit before we do our derivatives. Okay, so same thing that we did with the roots, the root and a fractional exponent. So we can rewrite this as x to the exponent 15 over, I'm not going to have space there. 1 second. Write this here. So x to the exponent 15 over 4, and same thing on the bottom, x to the exponent 5 over 4. Okay, subtract the exponents, just like we have x squared times x cubed, that's x to the exponent 2 plus 3. If the same base is being multiplied, we add the exponents. Here, if we have the same base being divided, we subtract the exponent. So this is x to the exponent 15 over 4 minus 5 over 4. And then we just simplify that thing 4. So that x to the exponent 10 over 4, x to the exponent 5 over 2, like this. Okay, so now it's reasonably simple or reasonably simplified. So we can do our derivatives from this point. So first derivative, 5 over 2. All right, x to the exponent 3 over 2. And our second derivative, 15 over 4, 1 over 2. This last one here, if we wanted, we could rewrite as square root of x. Doesn't matter, it's the same thing. So sometimes we want to simplify before we do our exponents, before we do our derivative stuff. As I just mentioned, it is possible to do the derivative directly using quotient rule, but this is a lot easier to do it this way. So find the most efficient way to do it. This didn't come up on the midterm because I didn't feel the midterm questions were especially difficult, but if I do put a question on a test that I think is maybe a bit harder or will take more time, I'll give you a little warning like this here, this little exclamation mark. All right, ready, next one. Okay, so theory question next. Do you remember what this definition of a derivative is here? Then prove that this thing is becomes this thing when it's a derivative. So most people forgot what this is. Take like 30, 40 seconds right now. Try to remember the definition of a derivative, the long thing with the limit in it. Try to write that out right now. Without flipping back at your notes during a test, you don't have your notes. You got to pull it out of your brain. Try to do that. I'll remind you that derivative is just slope. It's a way of calculating slope. That was for a different question. Okay, so definition of a derivative. So remember, an original function, if it's this, the derivative is just the thing that tells us the slope. So it's basically our slope formula. So do we remember? Does anyone remember? Oh, okay, so that's the original slope formula, the y2 minus y1 over x2 minus x1. So that's where it comes from, but we had some different ways of writing it. Does anyone online remember the full thing here?
Limit approaching 0. F
Okay, so
a plus h minus a over h.
0. Yeah. Sorry, tell me the rest of it again.
F a plus h minus f a over h.
Okay, so just a little difference. That was for a specific point. but most of the time we dealt with this in the more general version. So instead of a plus h or f of a, just f of x, just the general version. So this is y2, this is y1, and then h is just delta x. It means the same thing. Okay, use this. Now look at this function here and try to prove that the derivative is just equal to a. So take another minute and try. Okay. All right. So so f of x we have. So in this thing, h is, we don't have to evaluate that because that's changing. So, but we need f of x plus h and we need f of x. So this is just basic idea of how to use this function notation. We're not like, the first step here doesn't involve derivatives at all. So just f of x is a times x. X is the variable, a is just some constant, we don't know what it is. So x plus h here. So the way that the function notation works is whatever is inside the brackets, then that is going in place of whatever here we've written as x. So these brackets, whatever is inside here just goes inside here instead. Okay, so that's, again, that's not derivatives. That's just basics of function notation. So this thing then is just a times x plus h. That's what was inside the brackets here. Okay, so just whatever is inside the f of whatever, that's going to replace what was written there for x before. So that's just what function notation is. That's how we write this thing, nothing to do with derivatives. If we bring that back over to our derivative thing here, then our first line limits as h approaches 0, f of x plus h is a times x plus h minus, and on the other thing is ax. I'll have that over h. So we will simplify. Just before we do that, what we will. So what is the goal of this? Okay, so we have an h on the bottom. What we want to do, the whole purpose of this is we want to evaluate the limit. If we evaluate the limits, then that would be, well, a of x plus, evaluate the limit when h is 0 minus a x all over 0. But if we do it now, we have this division by 0 problem, math problem. We can't do that. So our whole goal here is to get rid of the h in the denominator at the bottom of the fraction there. So in this case, it's really not that hard to just do some rearranging and get rid of it. So what's the first thing we would do? Okay, so we'll expand here, open up these brackets. We'll have ax plus a h minus ax over h. And okay, so the ax minus ax cancel out, AH over H. And then limit H approaches 0 of A. The two H's cancel out. And final step. Okay, so we substitute H equals 0 into this thing, but this is like the easiest version. There's no H there. So just the limit has no meaning. So it's just A. So f prime of x is A, and we have proved that. So now for any function, if we have 5x or something, our derivative is just 5. So this is the proof. So that's how we use this. If we remember how to use this function notation, the stuff that I have on the right, and just substitute that stuff in and then just simplify. That's the basic process. Okay, next question. Critical points, so turning points for each of these. Again, we'll do A and B first. I'll give you 2 minutes to work, A and B, and then we'll look at C, D after that. Turning points, inflection points. Okay, that should be enough time to solve A and B. We'll look at those answers and then we'll come back and look at C and D. I'll give you some more time to work on those. So A, y equals 15x. I can know the answer without touching the derivatives at all. What is it? No turning points? And no inflection points because it is a straight line. The slopes are never changing, so it never turns to be negative. It doesn't have any sort of curving happen at all. We can say it's just a straight line. If we did want to show this with our derivatives, first derivative is equal to 15, and then we set this equal to 0, and we try to find where 0 is equal to 15, but that can never happen. We okay? So this can never happen, which is our math way of showing that there are no turning points at all. All right, and with our second derivative would be 0. So remember, where second derivative is 0, that means slope is not changing at that point. But it's not 0 at one point is 0 everywhere. So the slope never changes. So it's a straight line. So there are no inflection points. So those are the ways that we can show this just from kind of some logic and then also with our derivatives. So we could just say like straight line, therefore no critical points. All right, next one, B here. So our original function TR is 500Q minus 5Q squared. We just find our first derivative, which is also marginal revenue, important to remember. Total revenue prime or marginal revenue. What is the first derivative? All right, 500 minus 10Q. Okay, set that equal to 0, and Q equals 50. All right, we are also asked to classify as a maximum or a minimum. How do we do that? Second derivative, okay, so total revenue double prime is equal to marginal revenue prime with n. All right, -10. What does that tell us? Okay, this is a maximum or a minimum? Okay, so this is less than 0. So this means, again, our function is curving down at that point. So if it's curving down and we have a flat slope, the only way for that to happen is for it to be a maximum point. So we have a maximum. So there's the turning point. What about inflection points? No, how do we know there are no inflection points? Okay, so second derivative is 10, -10. If we set that equal to 0, we'd try to find where 0 is equal to -10, but that doesn't happen, so no inflection points there. So one maximum, no inflection points. All right, I'll give you some more time to work for C and D. Those are a little harder, so try to find turning points and inflection points for those ones. Take another 2 or 3 minutes. All right, a few more seconds to work. Okay, let's start with C here. What do we think? How many turning points, how many inflection points? 2 turning points, 1 inflection point. Yes. Okay. All right. So let's remember what the types are here for inflection points. We could have this thing where we have an inflection point here. We have curving down and then curving up afterward, and nearby turning points. We could have a situation like this. Let's redraw that. With this situation, we have an inflection point here because we have this curving down to curving up. Are there turning points? So in this one, no turn, or at least no nearby turning points. There would have to be another inflection point before there could be a turning point. So it is possible to have inflection points with no turning points. And then the last one is the special case where it goes perfectly flat. So we do have an inflection point here because we have curving down to curving up. Slope goes perfectly flat, but it never actually changes to the other direction. For the heat, I thought you were trying to be on camera. Okay. So in this case, we'd do our turning point test and we'd say, hey, we have a turning point here. But then when we do our inflection point, we realize, it's not a turning point, it's actually just an inflection point. So 3 possibilities, we need to keep those in mind when looking for these. All right, so our original function, total cost, 1/6q cubed minus 10q squared plus 300q. And our first derivative, marginal cost, 1/2q squared minus 20q plus 300. And we set this equal to 0. Q plus 300. And if we want to try to solve this, what would we do? Okay, so we'll factor out the 1/2. So q squared minus 40 plus 600. Okay. 40q, yes, thank you. 40q plus 600. So the way that we did these before, it won't always work, but we can try some product. Can we find 2 numbers that add to be -40, but multiply to be positive 600? So we can look at it, think about it for a bit. Probably you guys did this too, and you didn't see any. Or did you? No? Okay. So then our shortcut method, some product didn't work. What other things can we do here? Okay, so we'll just use our quadratic formula and that big long thing, the negative e plus minus square root e squared plus minus 4ac over 2a. And we'll just substitute in our parts and see what we get. So we have positive 40 plus minus b squared, negative 40 squared will be what? 1,600. Okay, that's the next part. So the next part, minus 4 times A, which is 1, times C, which is 600. So minus 2,400. And all of that divided by 2 times 1, so just 2. We should notice something at this point. Okay, so negative in the square roots, this thing is a problem. So the only solutions are imaginary numbers to this. We have no real solutions to this thing. So basically tells us there's no Q value that we can substitute in here that will give us 0. So no solution. And what does that mean about turning points? No turning points here. No turning points. So remember from what we just saw, just because we have no turning points, we could still have inflection points. We need to check for that independently. So we'll do that. I'll have to write over here. So our second derivative, Q minus 20, and we set this thing equal to 0, and we get a very simple Q equals 20 out of this. So it does look like we have an inflection point with no turning points. So we have, again, that kind of thing happening. If we remember in class, I mentioned that these total cost curves, like basically always will have this kind of pattern, an inflection point with no turning points. So that shouldn't surprise us in this case here. Okay, that took all the space and oh no. Oh, that does. Okay. All right, never mind. Fixed. Think online. Everyone can still see the questions and everything online.
Yes, sir.
Yeah. Okay. I messed up something with the TV briefly. Anyways, so that's this one, and we can look at the last one here, D. Already. All right. So D here. I'm not going to write out the original function. Let's just go first straight to our first derivative, which is what? X cubed plus 3 over 4x squared. And we set this equal to 0. We get 0 is equal to x cubed plus 3 over 4x squared. And how can we try to solve? Okay, so factor out the x squared here. So x plus 3 over 4. And then our two solutions for x. All right, so x will be 0 or x will be equal to negative 3 over 4. Okay, so two of these points here. And next we'll do our second derivative test. So our second derivative is plus 3 over 2 x. Okay, so there is our second derivative. We'll substitute in these points here. So f double prime at 0 will be equal to just 3 times 0 squared and then 0 here. So just we'll skip all that detail. It actually just turns out to be 0. So what does that tell us about this point where x equals 0? Inflection point. And is it a turning point? Is it an inflection point and a turning point, or only an inflection point? Only an inflection point. It's one of those special cases. So again, this kind of false turning point, it tricks us here. We think it is, but then we look and we realize that it's only happening where the second derivative is 0. So it's not actually changing directions at that point. I'll draw the graph of this in a moment. Question? Right. Is an inflection point not a turning point? We were doing a second derivative test on the turning point, but then we got this special case where it turns out to be 0. So let's do the other one, and then it'll probably be a little more clear. So 3/4. So second derivative at 3/4, 3 times 3/4 squared plus 3/2 times 3/. Yes, sorry, thank you. -3/4, -3/4. All right, what's our result of this? It's positive or negative? Okay, so this whole thing will be positive. This first term will be a larger positive thing. This will be a smaller negative thing. So the result is positive. Okay, so second derivative test, what does that tell us about this point? X equals. Okay, so this will be a minimum. So this is how our second derivative test usually goes, that we get it's greater than 0 or negative, or sorry, less than 0. But in this case, for the other one, we had this kind of, we found that it was actually exactly equal to 0. So we kind of accidentally found one of these inflection points. Let's see if there are any other inflection points. So and using our second derivative, which we said 3x squared plus 3/2x. And we set this equal to 0. So 3x squared plus 3/2x. And if we try to solve this, what can we do? All right, let's factor out the 3 and an x. And we are left with x plus 1/2. Okay, so our solutions here then, x equals 0, or x is equal to -1/2. So this x equals 0, here's kind of our normal way of finding the inflection point that we sort of accidentally found over here. And then that's also here. And then it turns out we do have one more inflection point here where x is equal to -1. Okay, so we have found the information, these critical points here. This is the second derivative. Second derivative is giving us inflection points. You're pointing here, this part, yeah. This is turning points. This is the second derivative test for the turning points, just to figure out if they are maximums or minimums. We have a conversation happening in the classroom here. Just want to make sure everyone's clear on this. Okay, So let me draw the graph of this for you. It will make a little more sense, at least when we have the graph. I'll have to erase some information here. So we said from left to right. So we have x equals negative 3/4 as a minimum. And then next we have x equals negative 1/2 as an inflection point. And then we have x equals 0 as a sort of special inflection point. Okay, so then I'm going to have to erase the rest of this. And the graph of this thing, zero. All right, again, it's going to be a little hard to draw nice smooth curves on this thing, but this is the shape here. So we have the minimum point here. We have an inflection point here because we have curving up, and then we have curving down, and then a second inflection point here where we curve back up again. And remember, the first derivative test doesn't really tell us turning points. It just tells us where the slope is flat. And we need that second derivative test to confirm it's actually a turning point. So we have a flat slope right here, and we have a flat slope right here. So the first derivative test told us those 2 points, and we had to do our second derivative test to see if they were actually turning points. This first one at negative 3/4, yes, was a minimum, but this other one at x equals 0 turned out to not be a turning point and only an inflection point. So that's the special case where first the both derivatives, where f of x will be equal to 0 and f prime of x, f double prime of x will be equal to 0. Make sense? Okay. Back when we did this derivative stuff, I had slides sort of summarizing each type of critical point and stuff, and then what each of the derivatives are at those points. So we can go back and look at that if we want. All right, a little more time. I don't think we'll finish the next one. Sort of an application with the demand curves and stuff. Let's at least try to finish A. So profit equations in these two scenarios here. That part should be all right. So take 2 minutes and try to figure that out. All right, let's look at the demand, or sorry, try to make the profit equations first. So two situations, universities and private labs. We'll do the universities one first. Okay, so this thing here, P equals 480 minus 6Q. What does that represent? Okay, so price it's our demand function. It's our relationship between price and quantity. And what do we need to do with this? Okay, we need a total revenue equation. So P times Q. So P will be this thing. So 480 minus 6Q times Q. So 480 Q minus 6Q squared. All right, and we've been given this total cost equation here already. I'm not going to rewrite that. So we can use those two things to make a profit equation. Again, I won't write out the two things originally. Tell me what the actual profit equation will be from our order of our biggest exponents down. -1/3Q cubed plus 9Q squared. Sorry, one more time. Minus 960Q. Wait, 960Q. $900. So we have no Q term. So we have a Q cubed, Q squared, no Q term. Okay. So 480 there, 480 there. Okay. So just by chance, those kind of canceled each other out here. But it does seem like this is working. So our dominant term, our leading term here is negative, but we do have at least one positive term. So this looks like the right kind of thing for a profit scenario. Let's do the other one here. So for the private labs, so our total revenue function here will be just Q times this thing. So 915Q minus 8Q squared. And then for that one, what will our profit equation be? -1/3Q cubed plus 7Q squared plus 435Q minus 900. Okay, so there are those two. Yeah, okay. We'll do we can solve B, the profit here for the university situation. For the private lab one, it gets a lot more complicated. So trying to find our max profits, then we set our, or we find our first derivative of our profit equation here, which will be so -Q squared plus 18Q. That's that. And we set this equal to 0. And what can we do here? Okay, so we can take out a Q here. So Q plus 18. And we have our two solutions here. So Q equals 0. Yes. negative q. Okay. And then our other one, q. Yes. Yeah. Oh, yeah. That's why I didn't have that before. Okay. So it doesn't. Yeah, it doesn't really matter. We can do it either way. If we factor out the negative q here, then this would be q minus 18. And then our solution here would be q equals positive 18. So we have these two turning points, it looks like. And we can do our second derivative test. So our second derivative for profits, negative 2q plus 18. And if we substitute in where q is equal to 0, I'll just skip actually writing it in. If q is equal to 0, our second derivative is positive or negative. Okay, so 18, so it'd be positive. So here we have a minimum point, and if q is equal to 18, then our second derivative will be what? Okay, so this will be a negative number, so we will end up with a maximum point here. So it looks like the maximum profit is coming here where q is equal to 18. The question asked us to find the number of microscopes to sell to maximize profits, which is 18, and also asked us to find price. How do we do that? Into which one? All right, so way up here, this demand function here, and then we could figure out what the price would be, which is, I'm just gonna look at my notes here, 372. That would be D. Part C here, it's the same process, but we're gonna have a bunch of roots that don't simplify, and the answer is just gonna look really ugly, but still doable. Okay, all right, so we got. Yeah. Why is? Because the numbers do not work out as easily. The numbers are not as nice. Yeah. So this one here, for example, there's no Q term. So when we did this first derivative, we didn't have to do like some product. We didn't have to solve a quadratic. We just had these two, so it's a lot easier. The other one is not. I'll very quickly mention the last question, which we don't have time to do for sure. I'm not going to mention what type it is. It was sort of a look at the situation and then try to be creative and think of which tool could work nicely in this scenario. It's on the slides. If you want a challenge, you can take a look at this one. This was like the final question off an exam from like a year ago or something. I think like maybe 2 or 3 people got it right. It was meant to be like the final challenge question on the exam. So if you want something fun to do over the weekend, you can take a look at this. So that's our review. Exam is coming up on Monday evening. Lots of you have signed up. Yes, lots of you have signed up to come do the exam in person. If you want to do that this week, like by the end of tomorrow. If you do it Monday morning, that's too late. I have to print everything off and all this stuff. So There's still more space. If you're going to come in person, fill out that form right away. If you're coming in person, we'll meet around like 6:45 or so. I think the rooms will be open, and then we'll like actually start, hopefully right at 7 o'clock. There's 2 hours to work. Yeah, 2 hours to work until 9 o'clock, and then just a bit of time to collect papers and stuff. Shuttles. The last shuttle bus is 7 o'clock. You'd have to walk home, I guess. Yeah. Okay. You can have a nice like walk home party. I walk home too. It's the same distance. So I'm, yeah, it's cold for me too. Okay. So that's that. We'll end here. If you have any questions about exam related stuff or whatever, I'll answer them once we finish here. Good luck with your studying and everything, and I'll see you guys for the exam. Goodbye.